Hello, everybody, and welcome to our seminar today. Today, we have with us Dr. Omid Asghari. Yeah, we practiced this before. So for today, we have the 3D modeling of subsurface soil features using geostatistics. In these presentations, the importance of modeling, interpretation of subsurface soil properties, and the implication of linear assumptions are first introduced. Following that, a brief introduction to the fundamental concepts of geostatistics will be provided. Variograms modeling and spatial continuity will be briefly discussed, and the Kriging estimator will be introduced. Geostatistical simulation and its role in uncertainty qualifications will also be briefly mentioned. A brief overview will be provided of geostatistical efforts addressing geotechnical features with the goal of addressing the challenges associated with linear assumptions. Toward the end, the introduced concept will be practically demonstrated using SGeMS software on a dataset showcasing the estimation of the SPT variable. So for today, our speaker is Dr. Omid Asghari. Yeah, who has a PhD in mining engineering, mineral exploration, and is a researcher associated in the PACS lab within the Department of Earth and Atmospheric Science at the University of Alberta. Prior to this, he was an associate professor in the Department of Mining Engineering at the University of Tehran and a visiting professor at the Center of Computational Geostatistics within the Department of Civil and Environmental Engineering at the University of Alberta. He has more than 15 years of experience in geostatistical modeling and data analysis on various sources of geoscience dataset. So with this, by the way, we have a problem, a challenge with this wire. We have changed the wire twice and it's still doing that, but I guess it's no huge deal. So yeah, with that, join me welcoming Dr. Omid.
Hello, everybody. Thank you. Omid Asghari, and I'm very happy to present this topic, 3D modeling of subsurface soil features using geostatistics. Mainly, we would like to discuss about geostatistics. I'm here as a research associate at Department of Earth Science, Permafrost Archive and Science Lab, PAX Lab. So let's, my biography was mentioned here, so I'm just skipping this one. Today, we are going to cover some important topics, why modeling soil feature is crucial in geotechnical design, the role of in-situ test and site investigation in building infrastructures, understanding permafrost, what is permafrost, and what is its impact, especially in thaw settlement situations. According to global warming, it would be an issue. Basics of geostatistics, including variogram calculation, modeling, and Kriging estimation. And after that, we're going to review some essential, some database related to SPT, standard penetration test, and one database for moisture content selected or sampled from cores in Mackenzie Valley related to PIN database. Okay, let's get into why understanding that what's under the ground is super important for geotechnical projects. To make geotechnical project work, we need to really get what's happening in the subsurface. Look at the pictures, including the Tower of Pisa. They show times when people got it wrong, what's under the ground. One big mistake is thinking the layers of soil go in straight line, but in reality, they have many variations, not only side to side, but only up and down. And to avoid this mistake and make geotechnical projects succeed, we need to do something differently. Just not linear interpolation. We need to go more, say, smarter estimation methods such as Kriging based on geostatistics, and we are trying to discuss a bit more. Okay, let's talk about how we explore what's under the ground for geotechnical projects to understand what's happening beneath the earth. We do in situ tests. It's like exploring by drilling holes in different site location. We use tests like the cone test or a standard penetration test to go. The goal of this test is to figure out how the soil behaves underground. All right, let's talk about checking what's under the ground when we want to build something like a road, like a bridge, like a big building. Imagine there's a piece of land and the owner or sometimes government want to use it for something new, but before they can design anything, geotechnical engineers need to know what's under the ground. So they drill several holes in the ground, kind of what you see here, and each hole gives us a report about the soil features there. And engineering sometimes use tricks like linear interpolation, as you see, and make the fence diagram to understand how the soil is laid out. Okay, let's talk about challenges we face with soil property modeling. The main issue is soil properties can change a lot in a short distance. And using linear interpolation, where we want to estimate what's between the two drill holes or 2 points, might make things too simple, especially when the soil is making different in a lot of directions. To fix it, instead of just using linear interpolation, we can go through different methods, and we prefer geostatistical method as something advanced, which can capture the variability over distance. Okay, using geostatistical, this figure shows some boreholes in a city of Iran. This data is SPT, and the color shows from say 0 blue colors to 50, the red ones. And the geotechnical interpolation method, we can create a non-linear fence diagram between two boreholes. 3D visualization of the soil properties can also be developed here. So we think that geostatistics provide more realistic visualization of subsurface profile. And you see the validation between the boreholes and the sections provided in simplified linear models. And geological engineers or geotechnical engineers can detect problematic soil variation, which would otherwise be not identified by linear interpolation. Okay. According to what I do at PAC's lab, let's go to permafrost and frost settlement. What is permafrost? Permafrost refers to a type of ground or soil that remains continuously frozen during the years for a specific period, typically 2 or more consecutive years. And permafrost is found in northern part in the region with cold climates such as high latitude and high altitude. And excess ice represent the ground ice that exceeds the pore space. Have a look at these two figures. On top, we have 5 sample 3 alluvial, 2 lacustrine samples, which are frozen. And if we keep these samples in room temperature for a while, it gets melting, the ice gets melting, and according to this melting, we see the thaw settlement according to the amount of excess ice content. For those samples which have very low excess ice content and do not see any sort of settlements, it could be negligible, but for the third on the right, there is around more than 40% excess ice content, so you can see that kind of thaw settlement. And this settlement can have significant implication for infrastructure built on. What we do at AXLab is to figure out the relation between different parameters and excess ice content. Finally, we want to predict or estimate with different sort of modeling, with different sort of regression modeling, linear and nonlinear. And here you see gravimetric water content in x-axis and the excess ice content on the y. And according to, for example, if you
Dr. Asghari, it's hard to hear you now.
Normally, for 1 meter of soil, we can expect around 30 centimeter of settlement. So it's very important for geotechnical design in northern region, especially in Yukon, Northwest Territory. And we're going to make a map of prediction excess ice content and say ground ice map of Canada during this project. Okay, let's dive into geostatistics, but not that much deep. Geostatistics was started in 16th decade by Kriging in South Africa in a gold mine, and Matteron in France, École des Mines, and the application of geostatistics was mainly founded in mining environment, and after a while it get popular. It became popular in petroleum, in environment, in geohazard, in forestry, fishery, or so many areas after a while. In geostatistics, we can use both continuous and categorical data. And by using any sort of geostatistical estimation, we can not only have in hand the estimation value, but also the corresponding error. We call it estimation variance. Here, we want to know what is variogram and how does variogram help us to capture the variability over distance. It's the main challenge in geostatistics to find or to calculate a useful variogram. We call variogram as a function of gamma. Gamma is a function of distance, and generally we know that 2 points which are very close to each other, the variable measured in these 2 points are somehow similar to each other, and by increasing the distance between these 2 points, call it pair, the difference or the variance increase and the similarity decreases. Variogram is a tool that captures, models this function, the variability over distance. and we can use this equation. Here we call it for distance h. H is a vector, connect two different points. The value of the second point, the value of the first point, in this condition, these they have so many pairs in the area. Observational, so by dividing, we can calculate the variogram for the specific distance. This figure is a schematic calculated for distance. Should be somehow very precise. It should be.
Sorry, it's very hard to hear again.
Geostatistics. And if we see here, there is three main parameters in variogram: the seal, the range, and the nugget effect. Seal, the plateau or maximum value of the variogram, which is equal to the variance of the whole samples, represents the total variability of the variable. And range is the distance of which the variogram reaches the seal, and the samples beyond the range, with distance beyond the range, are no longer correlated. So if we here, with distance over the range, they are not correlated, especially. And the nugget effect is the intercept of the variogram at zero distance, which represents the spatial variability at very, very short distance, or it's kind of a measurement error. Okay, let's have a look at this figure here. The white one variogram is over a distance, which means variation, but then for negative direction, something is decreased. Decreases over variogram. There is a very simple equation. Variogram, total values for people, and the point. Sometimes for the next step, we use variogram, or we can use as well the coverings between two samples. These are the popular mathematical models that we normally use in geostatistics. The first one is spherical. The first one is here. This one is a spherical model, exponential model, Gaussian model, and power law. All these diagrams have the same range and the same speed. But if you have here, for example, if we pick distance 10 and draw a line to cross-cut the variogram model, and then draw a value from variogram, you see it's around, say for this case, it is around 0.5. But Another equation shows something else, something different. It's around 0.6. In Gaussian model, it's around 0.3. That's the difference between the variogram that we have in our environment. If we have more continuity in our environment, the slope of this line is lower than, for example, this that at very longer distance they are correlated. Okay, let's go to estimation method. We normally use inverse distance in many estimation methods and Geostatistical. I think most of the estimation method we want to use for estimating the rate point, having 5 different observations with different distance. So we can use this function to predict or estimate the value at unsampled location. The weight is proportional to the inverse of the distance. Sometimes we use different powers. Use power 2, and according to this equation, the estimation would make it for another estimation method is estimator. We pick one data as the nearest sample to the distribution of the distance. What measurement we pick or estimation of this point? Red location, it would be 33, 22, 34, 27, 30. Which one? Which one is the closest? These are the distance. 1, 4, 2. Yeah, 34 is the estimation of location, unsampled location. Okay. In geostatistics, we would like to estimate the block or point with something a bit different. We're using Kriging method as the best linear unbiased estimator in geostatistics. Why we call it linear? It's obvious that everything is linear in this form. Here, that K is the estimation value, summation of different weights multiplied by the observations. Observations are around or in neighborhood of the point or location or block that we are going to estimate it. Why we call it unbiased? Because in ordinary Kriging that we are using, the summation of lambdas is 1. So we are not going to over or underestimate the value. And why we call it the best? Because in the context of Kriging, it refers to the fact that among all different linear unbiased estimators, Kriging minimizes the variance of the estimation error. So we call it the best. And we have so many Kriging methods, but we are going to just go through simple and ordinary Kriging in this talk. As I mentioned, simple Kriging methods, simple Kriging, the summation of weights do not sum to unity. But in ordinary Kriging, sum up to 1 unit. In simple Kriging, we use the average of the entire data set as a mean value in this equation. For example, unknown first and we want to give based on some data. There is a configuration of the data set here. One configuration for symmetry first to solve this equation. The distance that they have with each other and the variable of model that we have in mind. One value are known for us. These values are known as well. The location unknown here and the distance between observation here. So this part of the matrix is known, and we can calculate the lambdas, lambda 1, 2, and 3, which is the weight of this sample, the second one, and the third one. And by substituting these lambdas in this formulation, we have lambda, and the values each observation have, the mean average of the entire data set, summation of weights. Typical Kriging is not 1, it might be 0.8 or 0.9, and easily we can calculate or estimate the unknown location, and also we can have a prediction of the variance or the error that this location, according to this configurational observation, may have. And this one is the ordinary Kriging. Here in ordinary Kriging, we assume mean, but unknown. So we are not going to use the mean value in the equation. And very important part, the summation of weights is equal to 1. So if it's 1, so we can remove this part, and the equation gets more simple. And here you will see one rule, and then the condition to make summation of make the summation of lambdas. We will talk a bit about SPT modeling in this presentation. The data set I used is of Iran, a city, in the scale of a city, more than 12,000 data of SPT, mainly from the surface up to say 20 or 50 meters in some cases, from 1,300 or 1,400 boreholes. If you're familiar with SPT sample, SPT test, these values, very low values, when the soil is very loose, 4 to 10 it's loose, 10 to 30 million, and more than 50 it's very dense. And the other database we are going to show you if we have time is PIN database. PIN database is a Permafrost information network developed by Geological Survey of Canada, more than 13,000 boreholes, more than 55,000 moisture content, and different sort of information such as depth, deposition, environment, location. And this database is done in 70s and it is for construction of a pipeline which starts from Fort Simpson, if I'm not wrong, to the Arctic Ocean. It's more than 1,500 kilometers probably. It's an area in Mackenzie Valley, and we are going to have a small presentation about Let's go to this. I hope this can let me show you something. Move the mouse. Yes. Fix. Um, which one? Thank you. The very we will show you how Kriging works. Here on the top left, you see configuration of data. Blue ones are observation, and the red one is the point that you're going to predict. It's white and value. Here is the Variogram model that we have, and each part you see the weight of the samples. Let's start from here. This is a new configuration of, for example, 6 different data. They have the same distance to the estimation point, and we're going to use Variogram model, spherical, -0, 100, 100. We can move it, we can change it to see what would happen, for example. But as long as the configuration of data is the same, or they have the same distance with each one, or with the sample that we are going to estimate, the weights are exactly the same. But if I just move one point here to here, what would happen? Here, since according to the new configuration, the sample 2 has more weight than the other samples, and the sample 3, which is behind the sample 2, is less weight here. This shows the prediction, means the estimated value, and the corresponding variance. We even in Kriging can have negative weights. For example, if our configuration is something like this, the model is what would happen. Sample 2 is covered, sample 3, so the weight of sample 2 would be negative. But the summation of all samples are 1 because we're using ordinary Kriging. And here you see the matrix that is solved according to the number of observations. It's easily to use and see how Kriging works with different configuration of data, with different variogram models, what sort of weights we have, and what would be the estimation value and say estimation value and estimation variance. If we use inverse distance function to predict the value for this configuration of data, we will have the same weights. But here, if we are using Kriging data and the distance that they have, the observation have with each one is very important here. If we use inverse distance, the weights would be exactly the same because they are all in virtual. But here you see that, for example, sample 3, which is in the middle of these two, and sample 6, they have less weights here. Okay, let's move to another part. I want you to show you something about the this software that I'm using is SGeMS, very simple but useful software. It's free of charge. You can download it and do whatever you want, from estimation to different sort of simulation. And this is this SPT data set, including say 12,000 samples. Just have a quick look at the histogram of these data. Yes. And the average of data, and by this sort of data, we can make a 3D modeling, and we can estimate by ordinary or simple Kriging. And I want to show you, if we have time, we don't have that much time. Let me show you a part of this project. I've selected this part to show you the details. This is exactly some part of the SPT database. And I've made a model for this. This is the whole queue with estimation of variables. And I want to go through the details of this 3D modeling. Let's have a quick look at this. I can make different sections and different X, Y, and Z axes. Just have a look at the samples and the model. You see everything is the shape of the exactly linear one. We use Kriging to show the spatial variability. And if you have a look by changing the vertical plane, you see this value changes from around minus 50 meters surface up to the surface. And if you just have a look at the estimation, you see that these dark colors, the blue ones, shows a low value of SPT. And if we go down by this plane, you see that we are facing with hotter or warmer colors, which shows the high value of SPT because of going to down because say increase in SPT. But generally in this part, on the left part, we have more SPT values in estimation model. Here are the module that we can use for simulation, different sort of geostatistical simulation methods and estimation, such as Kriging, indicator Kriging, co-Kriging, which we are not going through the details of this one, and we can use this part of the software to input data and have it estimated. And the other database, let me show you. I can show you the details if we have time, but right now I want to just cover all of what I have prepared for this presentation. This is part of Mackenzie Valley database. Let me show you the whole database here. This is the whole database of PIN. Here is forget from Fort Simpson here, yeah, from Fort Simpson to Arctic Ocean. Yeah. It's around more than 1,000 kilometers, different boreholes. These are samples taken from Mackenzie Valley. So here, show you some details. These are boreholes taken from and samples taken from these boreholes. And the histogram of, say, moisture content. Here, moisture content from 0 to 50. These parameters is the same as SPT. By going down, the moisture content is decreased. So there is a trend in vertical direction. We see high values of moisture content on the top of the borehole, and on the say 2 meters or 5 meters of the first of the borehole, but by going down, the moisture content decreases. So here we have a trend in vertical direction, and just have a quick look at the model. Yes, this is a model estimated from this sort of data, and we can go through the variogram estimation or variogram calculation if we have time. Just have a quick look at these sections. In different directions. This section here, it shows section X and Y direction, and just show you something interesting. By going down in vertical direction, we expect a lower value of moisture content because of the reason I mentioned. Let's go down, let's go up. This is top of the model. We see high value of moisture content. First, high meters down, but by going down, this value gradually increases. And the modeling of moisture content and corresponding excess ice content, and therefore thaw settlement would be interesting, would be necessary according to global warming for geotechnical design. That's it. Thank you for your attention. Here.
Geostatistics of diagrams of spherical exponential accounts. And the question is to which situation we're setting.
Good question. If the say variation over distance is too much, we mainly use exponential model. Shows the high increase of the variance. If we go back to the presentation, it's still high variation over distance in where a bit, but this is yes, so some cases, according to the variability tree, use exponential. In some cases, we use spherical. But in areas that the variable is very, how to say, there is not that much variation, or it is continuous over over distance, we mainly use those series. For example, in petroleum industry, the parameters doesn't change that much, and there is a lot continuity in the environment. So the parameters such as porosity use shape because they are very similar over distance. But in some cases, this point is actually different. So it means by just a bit going further, value goes very high. Other shape. At first, we have to calculate the value now. We can do it here if we have time. And according to the configuration of our calculated variogram, we're going to make the best model according to our experience, and it's kind of visual fitting over the calculator and picks which one best.
Mission. I'm curious if you compared your ground ice for predictions with terrain analysis. Looking at the legal ground ice ledges, nice freeze factor like graded street ones, and see how well the geostatistical model compared to what the terrain analysis for areas of high ground ice.
Very good question. During this long distance, we have different trains, but it is just very quick model, and I didn't apply different sort of trains in this model. It's better to make different domains for each train, and according to this similarity within each train, make another in detail variogram model. You're right.
Any other questions there? We have a question from Eva. Can you unmute yourself?
Hello, you have my voice? Do you hear me? Yeah.
Yeah.
Yes.
Thank you, Dr. Asghari, for your presentation. I have a question. Actually, I have two questions. First one regarding to capture the variability of the soil in the practical, because in the most practical problems, there are lots of the variability that we can see in the field, which basically going through the simulation through last 2 decades. There is a tendency toward using a simulation, sequential simulation and MPS, multi-point simulation. What is your recommendation in the practical way when we want to use we want to model the geological and create our geological model? Your recommendation is, because as you know, the Kriging try to estimate the best answer, which in the practical maybe we are dealing with a different kind of the soil layers. We don't know about that, and most of the research and the new works going toward the simulation stuff. How we can deal with this, because as you know, using a Kriging estimation, it is a straightforward. Easily we can, not easily, but is a most less time consuming that we can get our geological model to using in the another way in the hydrogeological to create a hydrogeological model. How we can deal with this problem of the smooth problem, actually the smooth geological model that Kriging make it. This is my first question, and my second question about the Kriging model validation, how we validate our model. Thank you so much.
Thank you. Thank you for your both questions. To answer the first one, most of my experience is in mining and 3D geological modeling and resource estimation. In that case, the reason of using kriging and simulation sometimes differs. I mean, in kriging, we are going to predict the value for a block or for a point that we can trust more in. But the reason of using simulation method, no matter sequential Gaussian simulation, sequential indicator simulation, or multiple point simulation, or many other advanced techniques such as plural Gaussian simulation, the reason is to quantify uncertainty. We do a lot of realization. We make different sort of realization. For example, we make 100 or more realization for showing the variability for different iterations and capture the variability for each block during this 100 simulation or 100 iteration. And then we can say, for example, this block is have very high variance or very high uncertainty, and this block has low uncertainty. But based on simulation, we are not going to design a mine, or we are not going to design something else because we normally use the estimated value that we are more confident on. After we, according to my experience, after we estimated the blocks with kriging, we can go further and quantify the uncertainty corresponding to each blocks. And for your second question, there are several ways for validating kriging a result. At first, we can use, cross-validation methods, such as leave one out or leave a group out, or a jackknife or something like this. And if we go further, and it's very important, we use different scenarios with different variogram models, with different neighborhood analysis. And one other method that we normally use is a QKNA, quantitative kriging neighborhood analysis. We change different variogram parameters, we change different number of samples taken from one borehole. We change, the octant of and the radius of search ellipse, and then according to the cross-validation method, we choose the best one. And finally, we can validate the results by visual validation. For a section that there is different boreholes within, we can overlay the block model, and visually we can see if the block model confirms the value at boreholes or not. And these are the ways that we can validate our estimation methods.
Thank you very much. Any other question here? No? Okay, so nice to have you during this term, and see you in January, hopefully.